Okay, we're talking low speed flow here. So it's incompressible. Imagine flow with a velocity, density, and pressure. And we send that into a box in such a way that the flow is going to come into the box and maybe swirl around and come out. But if we follow one streamline, it's going to go to a point where the velocity is 0. It's going to come to a dead stop. Oh, we're going to call this, sorry, V0 because it's a point where the velocity is 0. And we're going to have a pressure here, P0. And we're assuming incompressible, so rho doesn't change. And we can write Bernoulli's equation between these 2 points in the flow. The flow out here and the point that we're subscripting 0. So that's the point out there, the main flow before it hits the box. And then at that point inside the box where the velocity is 0, we write Bernoulli's equation. And we see that the pressure has gone up as the flow slows down, which we know. So velocity goes down, pressure goes up. And so we're going to call this pressure when we slowed the flow all the way down to 0, which we can calculate. We're going to call this the total pressure. And the only way you can measure that pressure is if you take the flow and slow it down to 0. But it is a property of this flow because we can calculate it based on the velocity and the pressure. So in a sense, we're saying, okay, here's the total energy in terms of pressure inside the flow. Here's the potential energy, P, and then the kinetic energy, V. And if we add both of those together, we get the total pressure. So it is a property of the flow. And then we're going to call this term here, because it shows up in Bernoulli's equation all the time, we're going to call that, I'm going to write up here so it's up higher. We're going to call this Q. And you can put pressure in quotes, but it's called dynamic pressure because if you slow the flow down, you get that much additional pressure from the velocity. And it is 1/2 rho v squared. So it's the pressure we could get from the velocity. So these are important definitions that you'll need throughout your career. The total pressure is this thing here. And in fact, this total pressure stays constant, right? It's the value if the flow slows down, you get P at a new point is equal to 1/2 rho v squared. That's just Bernoulli's equation. This is a property of this flow based on the velocity and the pressure. So you'll need to know the formula and the definition for total pressure and also dynamic pressure. Yeah. Yeah, exactly, because you're holding it out there and you feel the air molecules hitting this side and this side, but then the air itself is slowed down and is pushing on your hand. All right, let's look at the units on that. they really are pressure. I think we worked the units on this before when we did Bernoulli's equation, but let's just remember. It really is pressure units. Has to be because we add it to P. But if we look at the units, this is kilograms per meter to the third, and this is meters per second squared. And so we can knock out one of these meters so that we get kilogram meter per second squared, and that's a Newton, right, by definition. So the units on this are newtons per meter squared, which is pressure unit. And like I said, we've done homework problems using Bernoulli's equation. When you work the units on that term, you always get pressure. So we can use this equation if we can measure both of these pressures, then we can calculate the velocity. If we put this box here and we put a pressure probe right here where the flow goes to 0, we get P0. And we can put a pressure probe out here and we can measure P, and the difference will give us velocity. Or we don't really care about measuring each one exactly by itself, we just want to know what the difference is. So if we can measure how much higher P0 is than P, then we can calculate the velocity. And in fact, this is an easy way to build a device to measure airspeed of an airplane. You have a Pitot tube that measures P0 and a static tube. I'm going to show you pictures of these that measures P. So the static tube measures static pressure, the Pitot tube measures total pressure, and you get the difference. So you hook up both those tubes to a manometer and you get the pressure difference, and you can calculate the velocity from this equation. So V is going to be P0 minus P times 2, work in this equation, divided by the density, and then square root. So one of these Pitot static tubes looks like this, and this is a picture in your book. Got the wrong screen there. Ah, here we go. So this is a Pitot tube. It's got a hole in the end, and the flow comes into the hole and stops. You guarantee that because you send it into this chamber. You can put a pressure gauge on that. That's the Pitot tube that measures this total pressure. And then you can put a Pitot tube combined with a hole on the side of a wall so that it only reads static pressure. There's no flow into the hole, so it doesn't get any of the velocity in there. And then you run it to a differential pressure gauge. Or you can combine the two together in what's called a Pitot static tube or probe. The flow comes into the end here, stops, and goes to a pressure gauge. And then this little side port measures static pressure. And you hook those up to a differential pressure gauge and you get the difference. So from this formula, we measure this difference here, and then all we need to do is know the density and we're good. In an airplane, it's not easy to measure density of a flow, because you have to grab a sample of the air and then weigh it in some way. So directly measuring the density is not easy, so often we'll use the density at sea level in the calculation or the instrument on board the aircraft. And if you do that, and you use this formula, you get something called equivalent airspeed. Because you're using the density at sea level, so you're getting the airspeed you would feel at sea level, even if you're flying at altitude. So it's not 100% accurate, but it's called the equivalent airspeed. And then if you use the actual density of whatever altitude you're at, say you're at 30,000 feet, if you use that, you get what's called the true airspeed. So this is called equivalent This is called true airspeed. So this is a device that you can use and is used on airplanes to measure the airspeed that the airplane is flying. Different than what you do with a car. The car is a mechanical device attached to the tire that's attached to the road, and you can measure exactly how far you go per second and get a velocity, right? But in the air, all you can do is measure the properties of the flow going past the airplane and get an idea of what your speed is.